Okay, so today, to begin with, I'd like to correct a mistake that I made at the very end of the previous lecture. Let me find this place. It's here. Okay, so at the end of the previous lecture, we proved the following theorem. If A is a commutative Banach algebra, then the Gelfand transform of A is defined in the following way. So the function A hat is the function on maximal spectrum, or equivalently on the character space of A. And this function A hat is defined by this simple formula. So when we identify a point in the maximal spectrum with the respective character, then the A hat of chi is just chi evaluated at A. So this is the definition of the Gelfand transform. And we proved that this function A hat is continuous on the maximal spectrum and vanishes at infinity. So now the Gelfand transform of the algebra is a homomorphism from A to the algebra C0 of continuous and vanishing at infinity functions on the maximal spectrum. And it has the following properties. So what I want to stress now is that when we look at the kernel of the Gelfand transform, it equals the intersection of all maximal modular ideals of A. So at the previous lecture, I forgot to say that we consider only modular ideals. And this is essential. In general, it's quite easy to construct an example. It's a nice exercise, by the way, to construct an example in which the intersection of all maximal ideals is strictly smaller than the kernel of the Gelfand transform. So we have to consider only maximal modular ideals. And this is clear from the construction, because by the definition of the Gelfand transform, its kernel is the intersection of the kernels of all non-zero characters. And we know that the kernels of non-zero characters are precisely maximal modular ideals. So the kernel of the Gelfand transform is the intersection of all maximal modular ideals of A. Okay. So today we begin to discuss Sistar algebras. So we start with the following definition. Suppose that A is an algebra, just an algebra without any norm. We define an involution on A is a map from A to itself, which takes each element in our algebra to another element denoted by A star, such that this map satisfies the following axioms. First of all, it is an involution in the usual set theoretic sense. That is, if we apply it twice, then we get the identity map. Second, this map is antilinear, in the sense that if we take the linear combination of two elements and then apply our involution, then we get the following. We obtain a linear combination, but with complex conjugate coefficients. Here, lambda and mu are complex numbers, and A and B are elements of our algebra. And finally, the involution is a ring anti-homomorphism, in the sense that A, B star equals B star, A star, for each pair of elements in our algebra. And an algebra with a fixed involution is called a star algebra. Star algebra. Okay, so this is a purely algebraic definition. Now let's come back to functional analysis. So we define a Banach star algebra, to be an algebra. First of all, of course, it's a Banach algebra. It's a Banach algebra equipped with an involution. So it is an algebra. It's a star algebra and a Banach algebra at the same time, such that the involution is isometric. The involution is isometric. Okay, and finally, let's give our main definition. And by definition, Banach star algebra A is called Sistar algebra. If for each element in our algebra, the following identity holds. The norm of A star A equals the norm of A squared. This identity is sometimes called the Sistar axiom or the Sistar identity. Well, I've already said at the first lecture that Sistar algebras were introduced by Gelfand and Nijmerk in 1943, and they used different terminology, and the notion of the modern terminology was introduced probably by Irving Siegel around 1950. Okay, so these are our objects. Now let's introduce morphisms between them. So suppose we have two star algebras, A and B. And an algebra homomorphism phi from A to B. Then we say that phi is a star homomorphism. A star homomorphism. If it is compatible with the involution in the following sense: phi applied to A star equals phi of A star for each element in our algebra A. And of course, we say that phi is a star isomorphism if it is a bijective star homomorphism. Obviously, in this case, the inverse map is also a star isomorphism. Okay, now before we look at examples of Sistar algebras, let's give one more definition. Suppose that A is a star algebra and B is a sub-algebra of A. Then we say that B is a star sub-algebra. B is a star sub-algebra. If it is stable under involution for each element B and B, the element B star is also in B. Well, it's clear from the definition that a star subalgebra of any star algebra is a star algebra itself. Moreover, if A is a Banach star algebra, then any closed star subalgebra of A is also a Banach star algebra. In particular, a closed star subalgebra of a C-star algebra is a C-star algebra itself. Okay, let's now look at some examples of Sistar algebras. Of course, first of all, we have a trivial example. The zero algebra is a Sistar algebra for obvious reasons. And the field of complex numbers is also a Sistar algebra. The involution on the field of complex numbers is just the complex conjugation. Okay, now let's look at a more interesting example. Suppose that X is any set. Then the algebra little L infinity of X of bounded functions on X, we know that it's a Banach algebra with respect to the supremum norm. But it is obviously a Sistar algebra. This is a Sistar algebra with respect to the following involution. So the involution is just the pointwise complex conjugation. And it's easy to see that all the axioms are satisfied. So it is a Sistar algebra. Now, if we suppose that X is a topological space, then we have the following chain of closed sub-algebras. C0 of X is contained in CB of X, and CB of X is contained in L infinity of X. CB of X is the algebra of bounded measurable, or sort of bounded continuous functions, and C0 of X is the algebra of continuous functions vanishing at infinity. So they are closed subalgebras, and moreover, they are closed star subalgebras. They're closed star subalgebras of L infinity of X. So they are C-star algebras. Among these examples, the most important one is the algebra C0 of X. And we will see soon that each commutative C-star algebra is of this form, is isomorphic to C0 of X. And this follows from the so-called commutative Gelfand-Naimark theorem, which will be proved, I hope, today, at the end of today's lecture. Well, one more example of the same kind. You will have a measure space, X mu, measure space, then big O infinity of X. We know that it's a Banach algebra, but it is also a C-star algebra. Again, with respect to the same involution. The involution is the pointwise complex conjugation. Okay, so far all these examples are commutative. The first and more or less obvious non-commutative example, which actually serves as a motivation to introduce C-star algebras, is the algebra of bounded operators on the Hilbert space. If H is a Hilbert space, then B of H, the algebra of bounded linear operators on H, is a C-star algebra. So let's recall that for each bounded linear operator T on H, the adjoint of T star, is a linear operator which is uniquely determined by the following identity. the inner product of t star x and y equals the inner product of x and ty for all x and y in our space. So it's a standard fact from functional analysis that this operation of taking the adjoint on B of H satisfies all the above axioms. So B of H becomes a Sistar algebra. This example, by the way, is important not only because it serves as the main motivation to introduce Sistar algebras, but also because of the fundamental result, also due to Griffant and Nymark, that each Sistar algebra can be isometrically embedded into B of H for some Hilbert space H. And we will also prove this result fairly soon. Star homomorphisms with values in B of H have a special name. They are called star representations. So if A is a star algebra and H is a Hilbert space, then by definition a star representation of A on H is a star homomorphism. Say pi from A to B of H to the algebra of bounded linear operators on H. And star representations there are many reasons why they are interesting. In particular, if we know some properties of representations of our algebra, then we know a lot of useful information about the algebra itself. And one more definition, we say that such a representation pi is faithful. Pi is faithful if the kernel of pi is trivial. In other words, faithful means injective for representations. In Russian, we usually say точное или верное. Okay, one more example of a non-commutative Sistar algebra. Again, if H is a Hilbert space, then the set of all compact operators on H, we know that it's a closed two-sided ideal in B of H. But we also know that the adjoint of each compact operator is also compact. So it is a closed two-sided star ideal. So this implies that it is a Sistar algebra. Which is not unital unless H is finite dimensional. If H is infinite dimensional, then of course K of H is not unital. Okay, let's now look at some counterexamples or non-examples. Example and exercise at the same time. Let's look at Cn of AB, the algebra of n times continuously differentiable functions on the closed interval. This is a Banach star algebra. With respect to the same involution as before. The involution is the pointwise complex conjugation. But it is not a Sistar algebra. It is not a Sistar algebra. Of course, unless n is 0. If n equals 0, then this is the algebra of continuous functions on the interval, and we already observed that it is a Sistar algebra. But if n is 1, 2, or bigger, then this is not a Sistar algebra. One more example, and again an exercise. Let's now look at the disk algebra A of D, which consists of those continuous functions on the closed unit disk, which are holomorphic on the open disk. So I claim that this is a Banach-Star algebra. This is a Banach-Star algebra with respect to the following involution. By the way, what is the involution? If I write the same formula as before, then this is not well defined for the obvious reason that the complex conjugate of a holomorphic function is not holomorphic. But if I also put the complex conjugation here over Z, then this is a well-defined involution, which makes the disk algebra into a Banach-Star algebra. So it is a Banach-Star algebra, but it is not a Sistar algebra. And another important example, which is related to harmonic analysis. If G is a group, we can consider the group algebra L1 of G. And we know that L1 of G, little L1 of G, is a Banach algebra with convolution product. In fact, it is a Banach-Star algebra. It's a Banach-Star algebra with respect to the following involution. It's a simple exercise to show that all axioms of a Banach-Star algebra are satisfied. But again, it is not a Sistar algebra. It is not a Sistar algebra, except for the trivial case where G contains only one element. Of course, in this case, L1 of G is just the field of complex numbers. So it is not a Sistar algebra, but on the other hand, there is a simple way to embed L1 of G into a Sistar algebra. So our next example is the so-called reduced Sistar algebra. Reduced group Sistar algebra. Again, we suppose that G is a group, and we consider the space little L2 of G, which is the usual little L2 space. So it consists of those functions f on G, for which the following series converges. The space of square summable functions on G. Of course, if such series converges, then this implies in particular that the support of f is at most countable. The little L2 space is a Hilbert space. This is a Hilbert space with respect to the following inner product. The inner product of two functions is given by the following series.
We're talking about discrete groups, right?
Yeah. Well, at this point, we consider groups which are not equipped with any topology. So we can always consider them as discrete group, as topological groups with discrete topology. In fact, this example can be extended to locally compact groups, but at this point, I wouldn't like to go into such details. Because this is just an example, we consider only discrete groups. But this example and, by the way, the group algebra little L1 of G, so all of them have natural extensions to locally compact groups, to arbitrary locally compact groups. Okay, so here's useful exercise. First of all, I claim that for each function f from L1 of G and G from L2 of G, their convolution is defined everywhere on G. Moreover, this function belongs to L2 of G, and the L2 norm of this convolution is less than or equal to the L1 or norm of f multiplied by the L2 norm of G. And moreover, if we consider the following map that's denoted by lambda from L1 of G to the algebra of bounded operators on L2 of G, which acts by the following formula. So lambda of f is just the convolution operator, which takes each L2 function G to f, the convolution of f and G, is a faithful star representation of L1 of G. This is a so-called left regular representation. So now we define the reduced Sistar algebra of G. The reduced Sistar algebra of G to be the closure of the image of the left regular representation. So this algebra is denoted like this. So this subscript little r means reduced. So it is the closure of the image of lambda in the algebra of bounded operators. So since lambda is a star representation, it's immediate that the image of lambda is a star subalgebra. So its closure is a C-star subalgebra of the algebra of bounded operators. So this is a reduced C-star algebra of G. The left regular representation becomes an injective star homomorphism from L1 of G to the reduced C-star algebra of G. An injective star homomorphism with dense image. By the way, when in a special case where G is abelian, it can be shown that this homomorphism can be identified with the Gelfand transform of L1 of G, or equivalent with the Fourier transform on our group. This will be an exercise in our first exercise sheet. Why is it called reduced, by the way? Well, in fact, there is another way to associate a C-star algebra to any discrete group G, which is defined in terms of some universal property, and which is called the full or just the C-star algebra of G, or the full C-star algebra of G. And in general, the reduced C-star algebra is a quotient of the full C-star algebra. But if the group is amenable, then the two C-star algebras are the same. But this is a totally different story, so I'll not tell you anything about amenability in this course. Okay, now let's discuss two useful constructions of Sistar algebras. Namely, let's discuss products and unitizations of Sistar algebras. The first construction is the product. And this construction is very easy. So observe the following. First of all, if we have two star algebras, A and B, star algebras, then their product, which is the same as their direct sum, is also star algebra. With respect to the obvious involution, defined as follows. So this is very easy. Second, if A and B are Banach star algebras, then their product or their sum is also a Banach star algebra. With respect to the following norm, so the norm of each pair, AB, is the maximum of the norms of A and B. And finally, observation 3, if A and B are C-star algebras, then so is their direct sum. So in other words, the above norm, the maximum norm, also satisfies the C-star axiom. Okay, so now let's consider unitizations.
You mean component-wise product?
Yeah. So let's now consider unitizations of C-star algebras. First of all, we observe that if A is a Banach star algebra, then so is the unitization of A. Namely, we define the involution on the unitization in the only possible way. So this is A star plus lambda complex conjugate 1. And we equip the unitization with the norm, which was discussed in the previous lecture, which is given by the following formula. So the unitization of a Banach star algebra is also a Banach star algebra. Now a natural question is, what if A is a C-star algebra? And here we have a problem. It's a simple exercise to show that if A is a C-star algebra, a non-zero C-star algebra, then the above norm on the unitization, let's denote it as 1. So the above norm doesn't satisfy the C-star axiom. Well, so this implies that if we try to define the unitization of a Sistar algebra in the same way as before, then we have a problem. The result will not be a Sistar algebra. Fortunately, there is another way to define a norm on the unitization of A, and to make it into a Sistar algebra. And to define this norm, we have to consider separately two cases: the case where A is unital and the case where it is not. So first of all, we consider the case where A is unital. And we observe that if A is a unital Sistar algebra, then we know that in this case, we have the following direct sum decomposition: A plus the one-dimensional ideal spanned by the difference of two identities, the new identity and the old one. And this is isomorphic to A plus C, and moreover, this is the star algebra is isomorphism. So they are isomorphic as star algebras. So now, since both A and C are Sistar algebras, we conclude that A plus becomes a Sistar algebra with respect to the following norm of A plus lambda times the difference of two identities is the maximum of the norm of A and the absolute value of lambda. Or equivalently, the norm of A plus lambda 1 is the maximum of the norm of A plus lambda, the old identity, and the absolute value of lambda. So the unitization of a unital Sistar algebra is also a unital Sistar algebra. Well, now let's consider a more interesting case where A has no identity. And in this case, we have the following proposition. Suppose that A is a non-unital. I'd like to stress that I mean strictly non-unital. Strictly non-unital Sistar algebra. So we assume that A has no identity. For each element A in the unitization, we define the left multiplication operator, LA. This is the operator from A to itself, given by the following formula. So A is an ideal in A plus, so LA is indeed an operator from A to itself. And we define a norm on A plus as follows. We define it to be the norm of the operator norm of the multiplication operator LA. So explicitly, this is the supremum of the norms of AB, where B runs over the closed unit ball of A. Then I claim that, first of all, this is indeed a norm. This is indeed a norm on A plus. Second, this norm extends the original norm on A. So for each element in A, the old norm of A equals the new one. And finally, if we equip the unitization with this norm, then we get a Sistar algebra. And this is a canonical way of making a non-unital, of making the unitization of a non-unital Sistar algebra into a unital Sistar algebra. Okay, now to prove this result, we will need a couple of lemmas. Lemma 1 and an exercise at the same time. Suppose that E is a normed space, and E0 is a vector subspace of E, a vector subspace of codimension 1. Then, if E0 is a Banach space, then so is E. So if a normed space has a codimension 1 Banach subspace, then it is itself a Banach space. And lemma 2, which is also a nice exercise, quite simple. Suppose that A is a Banach algebra equipped with an involution. Such that we have the following weakened Sistar axiom. The norm of A squared is less than or equal to the norm of A star A for each A. Then A is a Sistar algebra. In other words, this inequality, if such an inequality holds for each element in our algebra, then the involution is automatically isometric and the Sistar axiom holds. This is an easy exercise for you. Okay, so let's now prove our proposition. It will be convenient to start with the second part. So let's show that when we restrict this new norm, at this point we don't know still that this is norm, but let's show that when we restrict this to the algebra itself, we get the original norm on A. So part 2. First of all, you have two elements A and B in our algebra. So the norm is by assumption sub-multiplicative. So we have the following inequality. If we take now the supremum over the closed unit ball, so little b now runs over the closed unit ball, and take the supremum, we conclude that the new norm restricted to A is less than or equal to the old norm. But on the other hand, if we substitute A star here, A star, then by the Sistar axiom, this is the norm of A squared, and this is the norm of A multiplied by the norm of A star. In other words, the above inequality is an equality in this case. So this implies that the new norm of A equals the old norm. Okay, so this proves the second part of our proposition. Let's now show that, let's now prove the first part. So let's now prove that this new norm, this norm on the unitization is indeed a norm. Well, first of all, it's immediate that this is a seminorm. So it's clear that this is a seminorm. And let's assume that it is not a norm. So suppose that little a is an element in the unitization, is non-zero, but this seminorm vanishes at a. And let's try to get a contradiction. So we write a in the following way: a is b plus lambda 1, where b is in our algebra, and lambda is a complex number. And observe that so we assume that a is non-zero, this means precisely that lambda is non-zero. This follows from the second part of our proposition, which is already proved. Because if lambda is 0, then since a is non-zero, this implies that b is non-zero. But the new norm on b is the old norm of b. So this implies that b is 0, and so a is 0. Okay, so this implies that lambda is not 0. Lambda is not 0. So now the the seminorm, sorry, of a is 0, which means that the multiplication operator by a is 0. The multiplication operator is 0. That is, for each element C in our algebra A, AC is 0. So explicitly AC is BC plus lambda C. And since lambda is not 0, we can equivalently write this formula as follows. Minus lambda inverse BC equals C. And this implies that this element in brackets, let's denote it by E, minus lambda inverse B, is a left identity in our algebra. Is a left identity in A. But now let's recall that A has an involution. And since E is a left identity, it easily follows that E star is a right identity. And it's a simple algebraic exercise to show that if some algebra has both left identity and right identity, then it is unital. And this is a contradiction, because we have assumed that A is strictly non-unital. It has no identity. So this contradiction implies that our seminorm is indeed a norm on A+. Okay, so finally, we have to prove part 3, which states that unitization becomes a Sistar algebra with respect to this norm. We apply lemma 1 to A+. So A+ is normed space. It contains A as a codimension 1 subspace, which is the Banach space. So lemma 1 implies that A+ is complete. So lemma 1 implies that A+ is a Banach algebra with respect to the new norm. So we have to show that it is a Sistar algebra. To prove that this is a Sistar algebra, we take any two elements, say little a in A plus and B in A. And let's try to calculate the norm of their product, or to estimate the norm of their product. So for convenience, we'll take the square of this norm. So this product sits in A, so we can use the C star axiom, AB star AB, which is equal to B star A star A B. Now, by the submultiplicativity of the norm, this is less than or equal to the norm of B star times the norm of A star A B. And by the definition of the operator norm, that is on the new norm on A plus, this is less than or equal to the norm of B star multiplied by the norm of A star A in the unitization and by the norm of B, which is equal to the norm of A star A times the norm of B squared. Okay, and if we now take the supremum over the unit ball of B, so we divide by the norm of B squared and take the supremum over the unit ball, we conclude that the norm of A squared is less than or equal to the norm of A star A. Okay, and now we apply lemma 2. So we proved exactly this inequality in the unitization, which implies that unitization is a C-star algebra. And this completes the proof. Okay, so in fact, this result can lead to some dissatisfaction. Well, indeed, we defined a norm on the unitization in two essentially different ways, depending on whether or not our algebra is unital. But in fact, we will see soon that if we have an arbitrary star algebra, then there is at most one way to make it into a C-star algebra. In other words, if a C-star norm on a star algebra exists, then it is unique. And so this implies that essentially, well, not essentially, but exactly, is the unitization of a C-star algebra is unique. That is the only possible way to define a norm on the unitization of a C-star algebra, to define a C-star norm on the unitization of a C-star algebra. Okay, now our next goal is to discuss some spectral properties of C-star algebras. And to deduce from them the first, or the commutative Gelfand-Naimark theorem. The first, or the commutative Gelfand-Naimark theorem. So we start with some definitions. Suppose that A is a star algebra. Then we say that an element little a in A is self-adjoint so the name explains itself, A self-adjoint if A star equals A. So another name for such elements is permission. A more general definition, we say that A is normal if A commutes with A star. And finally, if our algebra A is unital, if A is unital, then we say that an element U of our algebra is unitary. U is unitary if it is invertible, and U inverse equals U star. Let's observe that each self-adjoint element is obviously normal. And each unitary element is also normal. So normal elements generalize both self-adjoint elements and unitary elements. And by the way, this is the main reason to introduce normal elements. So if we prove something for normal elements, then our result will be true in particular for self-adjoint elements and for unitary elements. And another observation, which is trivial but which is very useful, for each element A in our algebra, the element A star A is always self-adjoint. This is clear from the definition of the involution. Well, let's look at some examples. Example 1. Suppose that A is the algebra of all functions on some set X. Or we can also take the algebra of continuous bounded functions on a topological space. Then an element that is a function f in our algebra is self-adjoint, even only if it is real everywhere. And f is unitary even only if the absolute value of f of x equals 1 for each x. This easily follows from the definition. So in our case, the involution is just the pointwise complex conjugation. Well, another example. An example and an exercise in functional analysis. Suppose now that A is the algebra of bound linear operators on a Hilbert space. Then an operator T on H is self-adjoint even only if the respective quadratic form is real. That is, this inner product of Tx and x is real for each x in H. So in general, the intuition here is that self-adjoint elements are analogs of real numbers. So both example 1 and example 2 explain that somehow self-adjoint elements are related to real numbers. And second, an operator U on H is unitary in the sense of the above definition, even only if it is unitary in the geometric sense of the word, that is, if U is bijective, and preserves the inner product. Okay, we have the following simple proposition, which again emphasizes the analogy between self-adjoint elements and real numbers. Namely, for each element A in our algebra, there is a unique pair BC of self-adjoint elements such that A equals B plus IC. So in some sense, B is the real part of A and C is the imaginary part. The proof is immediate. We simply let B equal to A plus A star over 2, and C is A minus A star divided by 2I. So clearly they are self-adjoint, and our relation holds. So and A equals B plus IC. And it's a simple exercise to show that they are unique. Okay, now let's prove something more interesting. We have the following result. This is Theorem 1. It's quite easy, but I call it a theorem because it is very important. So suppose that A is a Sistar algebra. A is a Sistar algebra, and little a is a normal element in A. I claim that the normal A equals the spectral radius of A. So let's recall that in the general case, the spectral radius is less than or equal to the norm. So I claim that for normal elements of Sistar algebras, the spectral radius is exactly the normal way. To prove this result, first of all, we observe that for each self-adjoint element in our algebra, we have the following equality, which follows from the Sistar axiom. Let's now extend this equality to normal elements. So to extend it to normal elements, we substitute here A star A. So we know that A star A is self-adjoint, so we get the following. Now the left-hand side of this equality by the Sistar axiom equals the norm of A to the power 4. And let's also look at the right-hand side. So we have here A star A, A star A. But since our element A is normal, we can write this also in the following way. This is A star squared multiplied by A star multiplied by A squared. This is true because A is normal. Or equivalently, this is A squared star A squared. And now we apply again the Sistar axiom to the element A squared. And this gives us the norm of A squared and again squared. And if we now compare this and this, we take the square root, and we conclude that the square of the norm of A equals the norm of A squared. Now, a simple inductive argument implies that the same is true for all powers of 2. So we have the following identity. So now we can calculate the spectral radius by using the Gelfand-Bergling formula. The spectral radius of A is the following limit . Of course, we can take a limit over the powers of 2. The limit will be the same. But now the previous line, this formula implies that each member of the sequence is just the norm of A. And this completes the proof. Okay, so the spectral radius of a normal element is equal to the norm. Let's now look at some corollaries. Corollary 1. If A is a Sistar algebra, then for each element A, the norm of A equals the square root of the spectral radius of A star A. This follows from the Sistar axiom and from the fact that the norm of A star A equals the spectral radius of A star A. So what is the meaning of this corollary? The point is that the right-hand side of this equality is defined in pure algebraic terms. I mean, this is the spectral radius. So this implies that the norm of a Sistar algebra is uniquely determined by its algebraic structure. In other words, we have corollary 2. If A is a star algebra, then there is at most one norm on A satisfying the Sistar axiom. Sorry, no, at most one norm on A, not this is not correct, by the way. At most one norm which makes A into a Sistar algebra.
In unital case?
Not necessarily unital. Because when we proved corollary 1 or previous theorem, we didn't assume that A is unital. The spectral radius is calculated. At the previous lecture, we defined the spectrum for any element of an algebra, which is not necessarily unital. We just took the spectrum of the same element in the unitization way, and the spectral radius is now defined in exactly the same way as in the unital case, and is calculated by the same formula as in the unital case. So theorem 1 and corollary 1 hold for each Sistar algebra, not necessarily unital. And so, in other words, we see that this corollary 1 implies that there is at most one norm on A, which makes A into a Sistar algebra. Of course, I don't claim that such a norm always exists. There are some obstacles, but if such a norm exists, then it is unique. Again, the completeness here is essential. So I don't claim that there is at most one C-star norm on A. And this will be essential when we discuss tensor products of C-star algebra. Okay, so equivalently corollary 2 equivalently, this means that each star isomorphism between Sistar algebras is isometric. Each star isomorphism between Sistar algebras is isometric. And also, if we now come back to unitizations, we see that the norm on the Sistar norm on the unitization of a Sistar algebra is unique. So the construction is different depending on whether or not the algebra is unital, but the norm itself is unique. For example, when we defined the norm on the unitization of a non-unital algebra, we used the left multiplication operators, but we could equally well use the right multiplication operators, and the result will be the same because of the uniqueness. Corollary 3 generalizes corollary 2. Suppose that A is a Banach star algebra, and B is a Sistar algebra. I claim that each star homomorphism phi from A to B is continuous, and the norm of phi is less than or equal to 1. So this is another automatic continuity result. We already know that all characters of a Banach algebra are continuous. Now we prove that each star homomorphism from a Banach star algebra to a Sistar algebra is continuous. To prove this result, we first consider an arbitrary self-adjoint element in A. Then phi of A is also self-adjoint because phi is a star homomorphism. And so the norm of phi of A equals the spectral radius of phi of A. But the spectral radius of phi of A is less than or equal to the spectral radius of A, because we can extend phi to a unital homomorphism between the unitizations to unital homomorphism from A plus to B plus, and we know that a unital homomorphism of unital algebras doesn't increase the spectrum. So the spectrum of phi of A will be contained in the spectrum of A, and so the spectral radius satisfies this inequality. But the spectral radius of A is less than or equal to the norm of A. And so we see that the norm of phi of A is less than or equal to the norm of A. So this holds for each self-adjoint element. Now we take an arbitrary element. And again, use the trick that A star A is a self-adjoint. So if we now calculate the norm of phi of A, for convenience, let's calculate the square of this norm. So by the Sistar axiom, this is equal to the norm of phi of A star phi of A, which is the same as the norm of the image of A star A. And because this element is self-adjoint, we already know that for self-adjoint elements, we have this inequality. And now by the submultiplicativity of the norm, this is less than or equal to the norm of A squared. So now we take the square root, and so this completes the proof. We see that the norm of phi of A is less than or equal to the norm of A. Okay, now our next result, Theorem 2, is about the spectrum of a self-adjoint element in a Sistar algebra. Suppose that A is a Sistar algebra, and suppose that little a is a self-adjoint element of A. I claim that the spectrum, or more exactly the non-unital spectrum of A, is real. So in particular, if A is unital, we see that the spectrum of A is real. To prove this result, we may assume from the very beginning that A is unital. Well, indeed, we already know that the unitization of a Sistar algebra is a Sistar algebra. So if A is not unital, we simply consider the unitization of A. So to prove that the spectrum is real, we take any element in the spectrum, and we so we write it in the following form, where alpha and beta are real numbers. So alpha is the real part and beta is the imaginary part. And we suppose that beta is non-zero. So we want to get a contradiction. Okay, so lambda is in the spectrum of A. So by the polynomial spectral mapping theorem, we conclude that for each real number t, lambda plus it sits in the spectrum of A plus it1. So the absolute value of this number, lambda plus it, is less than or equal to the norm of A plus it1. Okay, so the square of this number is less than or equal to the square of this norm. Well, now what is this? We now apply the Sistar axiom. So the adjoint of this element is A minus it1, because A is self-adjoint. So the Sistar axiom implies this. So what is this? This is nothing but the norm of A squared plus t squared 1. And by the triangle inequality, this is less than or equal to the norm of A squared plus t squared. Okay, now let's now look at the left-hand side of this inequality. So what is lambda plus it? This is alpha plus it plus I beta. So the square of the absolute value of this is the sum of the squares of the real part of the imaginary part. So this is lambda squared, alpha squared plus beta plus t squared, which is alpha squared plus beta squared plus 2 beta t plus t squared. Okay, now we compare this and this. So we see that this number is less than or equal to this number. So after we cancel t squared, conclude that alpha squared plus beta squared plus 2 beta t is bounded by the normal A squared for each real number t. But if beta is not 0, this function is not bounded from above. And this is a contradiction. And this contradiction implies that beta is 0. That is, lambda is a real number. And this completes the proof. So the spectrum of a self-adjoint element, in a Sistar algebra is always real. Okay, I see that it's time to finish. Unfortunately, I had no time to prove the Gelfand-Naimark theorem. So at the next lecture, we deduce some corollaries of this result, of the fact that the spectrum of a self-adjoint element is real, and we prove the commutative Gelfand-Naimark theorem, which states that for each commutative Sistar algebra, the Gelfand transform is an isometric star isomorphism of A onto C0 on the maximal spectrum. So essentially, all commutative Sistar algebras are of the form C0 of X for some locally compact Hausdorff topological space X. Then we discuss some category theoretic interpretation of this result and discuss the continuous functional calculus in Sistar algebras. Okay, so that's all for today. Thank you.